All right, good morning and welcome to Master Talker online class. In today's video, we'll be talking about linear momentum. All right, linear momentum is momentum in a straight line. In fact, the word linear means straight line. All right, the momentum of a body is the product of the mass and its velocity. So you should know that momentum is equal to what? Mass times velocity. And don't forget that mass is measured in what? In kilogram. While velocity is measured in meter per second. So the SI unit is what? Kilogram meter per second. All right? Kilogram meter per second. So that's the SI unit of momentum. All right? So, right. Momentum is a vector quantity. All right? That is, it has both magnitude and direction. Meaning that momentum is always along a straight line. Okay? This momentum represented by P is equal to mv is sometimes called linear momentum to distinguish it from angular momentum. All right, this one that has mass times linear velocity is called linear momentum. In fact, linear momentum is equal to what? Mass times the normal velocity, the linear velocity. That's why we say that it is what? mv. But angular momentum is equal to what? Mass times angular velocity. So we say that what? That is what? Mass and what? Omega. Okay. So this one is measured in what? Kilogram rad per sec. Why this one is measured in kilogram meter per second. So this one is measured in kilogram rad per sec. Why this one is measured in kilogram meter per second. So now let's talk about the Newton's law of motion. Okay, Sir Isaac Newton was the first to discover how forces are related to motion. He stated three important laws of motion. The first one stated that is the first Newton law of motion. The first Newton law of motion stated that a body will continue to be at rest or in a uniform motion in a straight line unless acted upon by an external force. So that's the first one. So the first one stated that a body will continue to be at rest or in a uniform motion on a straight line unless acted upon by an external force. Yes, this board will continue to be here until maybe I decide to shift it. I apply a force to shift it. If not, it will remain here. Then a body that is on a car that is moving on a straight line will continue to move on that straight line unless maybe I decide to apply a brake or maybe another car comes to hit it. Once there's an external force, that is when it will change its position. All right. So the next thing we'll talk about is inertia. All right. Inertia is the tendency of a body to remain in their state of rest or in a uniform motion on a straight line. So inertia is the tendency for a body to remain at rest or in a uniform motion in a straight line. All right. That is inertia. Now, inertia is inherent in a body at rest or in the one in a motion. That is, a body at rest is reluctantly to move. Anybody at rest is reluctant to move. It is at that place. The tendency of it to remain there is what is called inertia. So, and the body that is on a straight, that is already moving, is reluctant to stop. Right there, is reluctant to stop. So, we now say that what? This is inertia of a body, and the inertia is a property of matter, and the mass is a measure of inertia. In fact, you should know that what? You should know that inertia is directly proportional to the mass. Okay, if the mass of a body increases, then the inertia will increase. Okay, so the ability to stop a train and to stop a car is not the same. You need more heavy force or brake to stop a train than the one to stop a car. All right, so that is that for inertia. Now, observation based on the Newton's first law of motion and inertia. And please note that what? That the first Newton's law of motion is equally called the Newton's law of inertia. Please, very, very important. The first Newton law of motion state is what? Is equally called the Newton's law of inertia. So they can tell you to state the Newton's law of inertia. It's the same as stating the first Newton's law of motion, which still stated that a body will continue to be at rest or in a uniform motion on a straight line unless acted upon by an external force. Now, observation based on the first Newton's law of motion and inertia. Number one, passengers in a fast-moving vehicle tends to jack forward when the driver suddenly apply the brake. They are also jacked backward when the vehicle suddenly speed off. This is this is why seat belts are used. All right. The reason you are using seat belt is because if something is on a speed and the person match the brake, you are tend to move, and if you don't have seat belt, you can easily the brake can even throw you out of the car from the glass, and you will injure. So that is why they tell you to use your seat belt so that it can hold you back. So number two said when there is collision between two vehicles, the passengers are thrust forward in the respective direction of motion. This is the reason seat belt is required again. Number two, an open side door of a fast moving bus closes by itself when the driver suddenly applies a brake, and that's true. So it is easier to put a car into motion than to put a trailer into motion. Like I said before, it is more difficult to stop a moving trailer than to stop a moving car. Yes, passengers jumping from a moving bus would have to run forward to continue in their state of uniform linear motion before coming to rest. Otherwise, the forward momentum will drag them to fall. Yes, that is why if you see a conductor that wants to jump out of the car, once he jumps, he starts running towards the same direction with the car before he decides to stop. But if you don't know about this thing and you just jump down, there is no way you will stand. You must definitely fall. That is why drivers will encourage you not to jump down until they stops. Okay. Why is it important that a defender in football should have a loss of weight? Yes. Okay. They said the role of defender is to stop attacker. An attacker runs towards a defender's goalpost with high velocity okay, which implies high momentum. The defender must have a great inertia to. Okay, they say, why is it important that a defender in football should have a lot of weight? Oh, if you're a defender, you're supposed to have a lot of weight so that you can be able to stop that attacker that is coming to you. All right. I like that question, and that's WAEC question. That is 2012/2011. Wow, that is GCE. Okay, that is inertia acting there. All right. So the second law states that what? Write the second law. The second law states that what? That the resultant force F causing a change in what? Momentum of a body is directly proportional to the time rate of change of momentum. All right. You can say that what? The force is directly proportional to the what? The rate of change of momentum. All right. That force, the resultant force causing in the direction of that force. So please, that the force applied to a body is directly proportional to the rate of change of momentum to the direction of that force. That is the easiest way to state it. That the force applied to a body, the resultant force applied to a body, is directly proportional to the rate of change of momentum in the direction of that force. So what are they talking about? That force is directly proportional to what? The change in momentum. The change in what? Momentum over what? Over time taken. Over the time taken for the change. The time taken for the change. Okay? Now, that's why they say that is the rate. Rate means time. The rate of change of momentum. So therefore, force F is equal to change in momentum is what? mv minus u. In fact, or mass times final velocity minus what? Mass times initial velocity all over what? Time. All right. Then you can bring your proportionality constant. You can bring in your proportionality constant. And if you look at this, you see that the mass are the same. So we now have that what? F, sorry, directly proportional. F is directly proportional to what? M in bracket of V minus U all over what? All over T. Right? If you bring in your proportionality constant, you will now have that what? That F is equal to what? K M in bracket of V minus U all over what? T. But here K is equal to 1. So if K is equal to 1, you have that what? That F is equal to what? M in bracket of what? V minus U all over what? All over T. Okay? But if you can remember that what? That acceleration is what? Change in velocity over what? Over time. You will now see where they got that formula that F is equal to what? M. Instead of putting V minus U over T, you put it as acceleration. So therefore, force is equal to what? MA. Very, very important thing to note. And another thing you need to note is that what? That from here, F is equal to this. Let me call this equation 1 and this equation 2. From equation 1, which is M in bracket of V minus U all over T. Then if I cross multiply that, I'll have that Ft is equal to M in bracket of V minus U. Can you remember what is Ft? Don't forget that impulse is equal to Ft. So impulse, which is equal to Ft, is equal to what? Change in momentum. So note that what? Impulse is the same thing as what? Change in momentum. Impulse is equal to change in momentum. So let us solve some calculations to illustrate what we have done so far. Okay. The first question I'm going to solve said a force acting on a body causes a change in the momentum of the body from 12 kg meter per sec to 16 kg meter per sec in 0.2 sec. Then they now say calculate the magnitude of the impulse. Solution. Okay, you should just know that impulse is equal to Ft, which is same as what? Change in momentum. Change in momentum. Okay, so it's equal to change in momentum. So what do we do? The change in momentum from here to here. So it will be what? mv minus mu. All right, and mv is the change in, that is kilogram meter per second. Kilogram meter per second. That is what? 16 from the final minus the initial. 16 minus 12, which is what? That is 4 Newton seconds. 4 Newton seconds. So that is that. So the next question. The next question. Question number 2. Question number 2. Question number 2 said that a ball of mass 0.1 kg moving with a velocity of 20 meter per second is hit by a force which acts on it for 0.2 seconds, 0.02 seconds. Then I say if the ball moves off in the opposite direction with a velocity of 25 meter per second, then say calculate the magnitude of the force. Calculate the magnitude of the force. Okay? Calculate the magnitude of the force. Solution. We know that what? That impulse, which is equal to what? Ft, is equal to what? Change in momentum. Okay? So therefore, the force will now be what? Change in momentum all over what? The time. So we have that m in bracket of v minus u all over what? Over t. So what do we have now? We have the mass as 0.1 in bracket of what? The velocity is 25 minus 20, then all over 0.01. So what do we have? 0.1 in bracket of 5, then all over 0.02. So if you do that, you will have okay, sorry. They say that what? That that this one moved in opposite direction. So if it is moving in opposite direction, then it will now be that v is equal to, what am I saying? That they say that what? A ball of mass, this is moving with what? This is the initial velocity he was moving with 20 meter per second. Okay, is hit by a vehicle. Sorry, it is by a force which acts on opposite direction. Okay, when they hit this one, it started moving in opposite direction. So the velocity here changes and started moving opposite. So the velocity I'm going to use should be what? Minus 20 meter per second. Okay, so that's the velocity I'm going to use. So I'm going to say 25 into minus 20. So what do we have now? We're going to have 0.1 in bracket of 45, then divided by 0.02. So if you do that, you're going to be having a 225 Newton. 225 Newton. All right. So the next thing we do is what? Let's talk about the Newton's third law of motion. The Newton's third law of motion states that what? Action and reaction are equal and opposite. Or you say that what? To every action, there is an equal and opposite reaction. To every action, there is an equal and opposite reaction. That is the third law of motion. So the next thing we're going to talk about is what? Conservation of linear momentum. Conservation of linear momentum. Right? They say that what? The principle, that is the law of conservation of linear momentum, is stated as follows. Right? They say that in an isolated system of colliding bodies, total momentum is always constant. Okay, that is conserved. Or if two or more bodies collide in a closed or isolated system, the total momentum before collision equals the total momentum after collision. Very, very important that in a closed or isolated system, that the total momentum before collision is equal to the total momentum after collision. All right, very important. Okay, a closed or isolated system is a system on which no external force acts, neither does itself act on any on another system or body. The principle of conservation of linear momentum can be stated mathematically as follows. Just say if a body 1 and 2 of masses m1 and m2 moving with initial velocity u1 and u2 respectively collides and thereafter move with final velocity of v1 and v2 respectively, then we now have that what the total momentum before collision should be equal to the total momentum after collision, and the momentum before collision, momentum before collision will be equal to what? M1 U1 plus M2 U2. So this is the momentum of the first body and the momentum of the second body. So momentum after collision should be what? M1 V1 is equal to what? Sorry, plus M2 V2. So what do we mean by that? Okay, so the change in momentum. Sorry, this is the change. The total. No, this is the total. The total momentum before collision is equal to the total momentum. So for the conservation of linear momentum, say that what? Momentum before collision is equal to momentum after collision. After collision. So what do we have? We now have that M1 U1 plus M2 U2 is equal to what? M1 V1 plus M2 V2. Okay, very important thing to note. This is the formula for what? The momentum or the conservation of linear momentum of what? The system, an isolated system or a closed system, please. That is a system whereby there is no an external force, no external force. That is when you use this formula. Okay, the above formula is used when the two bodies moved in the same direction before and after collision. Very important thing to note that whenever they are in the same direction, okay, that before and after collision, that's when we use that. Okay, now if two bodies moves in opposite direction, in fact let me draw this thing. For this one is I have the first body, this is the first body coming this way, and then the second body coming this way. This one was moving with M1 U1, then moving with what? M2 U2. All right, then resultantly they now collide. The both of them started moving together like this. So we now have that what? In the same direction I have what? M1 V1 plus what? M2 V2. So that is for this. That is for this. Okay. But the next one, this is number one. Now for number two, now if they are now moving in opposite direction, this one is coming this way and this one is coming this way. All right. This one is coming with M1 U1 and this one is coming with what? Minus M2 U2. Yes, because it's coming in opposite direction. The velocity will be negative. So it will now be equal to what? They will now collide. When they collide, they will start moving in one direction. It's either if this one is stronger than this one, they will move in this direction. But if this one is stronger than this one, they will be moving in the other direction. So they are moving in one direction. Let's assume that they are moving this way. You will still have this same result because they are moving in the same direction plus M2 V2. That is very important thing to know. So you have that what? M1 U1 minus M2 U2 is equal to what? M1 V1 plus M2 V2. Okay, this is when they are moving in opposite direction. All right, they say if two moves in if the two of them moves in opposite direction before collision and both move in the same direction after collision, this one is when they move in the same direction. They here they move in opposite direction, but here they started moving in the same direction. But there is a way. That is number three. Number three now is that if they are moving in opposite direction, watch. If they are moving in opposite direction and when they collide, when they hit each other, as they hit each other, they scatter. They move in different direction. This one started moving this way. This one started moving this way after hitting each other. So what do we have here? What do we have here? We still have that what? M1 U1, and here will be minus M2 U2. Will now be the same thing here. M1 V1 and minus M2 V2. All right. So we now have that what? M1 U1 minus M2 U2, okay, is equal to what? M1 V1 minus M2 V2. So please, you should be very, very careful with what they stated in the question, whether they are moving in the same direction or not. Okay. So that is very, very important. These are the three most important formula you need to know for linear conservation of for the conservation of linear momentum. Let us state it again. The first one is when both of them are moving in the same direction, you have M1 U1 plus what? M2 U2. In fact, the same direction means plus, opposite direction means minus, and they now collide. If they collide and started moving in the same direction again, you will have that what? M1 V1 plus what? M2 V2. Please, very, very important. Now the next one is, the second one is when they are moving in opposite direction, they are moving opposite to each other, okay, and opposite there must be minus. I'll have what? M1 U1 minus M2 U2. Then when they hit, they started moving in the same direction, I'll have M1 V1 plus M2 V2. All right. Then the last one is that they were moving in opposite direction, so I'm supposed to have M1 U1 minus M2 U2. Okay, when they collide, they started moving in opposite direction again, so I'll have M1 V1 minus M2 V2. All right. So these are the three main important formula you need to know for linear conservation of, for the conservation of linear momentum. Sorry, for the conservation of linear momentum. So the next one we'll talk about is what? Elastic collision. Okay, let's talk about collision. Okay, collision. There are two types of collision, namely elastic and inelastic collision. So let's talk about the first one, elastic collision. Elastic collision. Okay, this is one of my best topics in physics. Elastic collision. All right, in an elastic collision, both the momentum and the kinetic energy are conserved. Please, very, very important to note that in an elastic collision, both the momentum and the kinetic energy are conserved. In a particular, sorry, in a perfect elastic collision, we have that, okay, in a perfect elastic collision, we have that M1, we have that M1 U1 plus M2 U2 is equal to M1 V1 plus M2 V2. All right. Then we now have that, and we equally have that for their energy. You know that what? That their energy are conserved as well. This one is the momentum. Then for their energy, you have that what? 1 over 2 mv squared. I hope you know that kinetic energy is equal to what? Half mv squared. So the kinetic energy of the first one will now be 1 over 2 m1 u1 squared plus 1 over 2 m2 u2 squared is equal to what? 1 over 2 m1 v1 squared plus 1 over 2 m2 v2 squared. All right. So that is that. So example of an elastic collision is what? The collision of a no, Birad balls, the collision of molecules, okay, a tennis ball that bounce back to its original length after hitting a hard surface. Okay, that's for examples of elastic collision. But let's talk about inelastic collision. Okay, for inelastic collision, right? In an inelastic collision, the momentum is still conserved, but the energy is not conserved. Please, the momentum is conserved, but the energy is not conserved. All right. So the kinetic energy decreases after collision. In this type of collision, the colliding bodies must not stick together and moves with one unit 1 unit after collision. That is, their velocities are the same. Okay, in an inelastic, in fact, the main difference between elastic and inelastic collision is that in an elastic collision, their final velocity are still different. They move with different velocity after collision. But in an inelastic collision, the final velocity become the same. They move with the same collision. In fact, they now join together and started moving with just one velocity. So for in an elastic collision, we have that what m1u1 plus m2u2 will now be equal to what m1 plus m2 moving with just one velocity. Okay, they will be moving with just one velocity. So it means that what the velocity of the second one is equal to the velocity of the first one, and then we call it just v. So in an inelastic collision, they move with what just one single what is it called just one single velocity after collision, right? So the same thing is applicable for their energy. For their energy, don't forget that kinetic energy is equal to what half mv squared. So I'm going to have what 1 over 2 m1 u1 squared plus 1 over 2 m2 u2 squared is equal to what 1 over 2 in bracket of m1 plus m2 then v squared. All right, so that is for their kinetic energy. So all right, so let us solve some calculations to illustrate what we have done so far. So the first question we are going to solve, the first question said fuel was consumed at a steady rate of 5.0 times 10 raised power minus 2 kg per second, okay, in a rocket okay. Before this, let us talk about the application of Newton's and conservation of momentum. The application, all right, where do we apply them? The first one is what? In recoil of a gun. The first one, please, before this, let's talk about the application. Okay, recoil of a gun. The first one, we apply it in recoil of a gun. They say that when a bullet is fired from a gun, the gun jacks backward. Okay, the gun jacks backward. The gun is said to recoil. In this case, Newton's third law of motion is is in operation. All right, so the forward momentum of the bullet equals the backward momentum of the gun. So therefore, the propulsive force on the bullet is the action, and the recoiling force of the gun is the reaction. So therefore, it is given by MB. MB is the mass of the bullet. The mass of the bullet. Okay? And the VB is the velocity of the bullet. Velocity of the bullet. Okay? So we now have that what? mg is the mass of the gun. Then Vg is now the velocity of the gun. Vg is now what? Velocity of recoil of gun. Okay? Then we now have that mov then MBVB is equal to what? The forward or final momentum of the bullet. The forward or the final momentum of the bullet. Okay? Then we now have that MGVG, that is the backward or final momentum of the gun. The backward. The backward or the final. The backward or the final momentum of the gun. So we are going to have that MBVB is equal to MGVG. Very important formula to note. All right. Now, this is obtained from conservation of momentum law as follows: that their initial momentum is equal to 0. Okay. All right. So, but before this formula, how this formula is gotten from is that that you know that the initial one, MB for the bullet, UB plus what? MG UG is equal to, now they were all in the same direction. The gun is facing this way and the bullet is facing this way. But when they fire it, the bullet moves this way while the gun falls back. So that is why we have, for the final one, we have that what? MBVB for the bullet moving forward, but the gun will now move backward. That's why we have minus MGUG. Okay, and then but we have that what? That the initial momentum is 0. Okay, this is obtained from conservation of momentum law as follows: that their initial velocity, their initial momentum is 0. So note that the initial momentum is 0. So if this side is 0 now, we now have that MBVB minus MGVG. VG is equal to 0. So if you now collect like terms, you will now have this particular formula. Okay, that's the first one, the recording of a gun. Then the second one said jack and rocket proportion. Okay, the principle of conservation of linear momentum and the laws, the Newton's third law of motion, are applied in the proportion of jets. Okay, they say jets and rocket proportion. Okay, they say that the principle of conservation of linear momentum and Newton's third law of motion are applied in the proportion of jets, aircraft, and rockets. Fuel enters the combustion chamber of the engine, where it is burnt, and the resulting gas are expelled through the tail nozzle at very high velocity. This gives the aircraft or rocket an equal and opposite momentum with which it moves forward. Okay, the forward thrust of aircraft/rocket is equal to the force at which the gas are expelled. So we have that the force for rocket, we have that force is equal to mv, mass times velocity for rocket. Okay, the mass times velocity, because their initial is 0. Now it's supposed to be what? That the force is equal to what? Mv minus what? MOU. Okay, but this one here is 0. Their MOU, the initial one, is 0. So the force is MOV. Okay, that is for rocket, please. Because it has rest. It is at rest. So number 3 is walking. Okay, when a person walks, the pushing against the ground with his foot, the ground is turned exact and equal and opposite force back on the person, which moves him forward. Yes, as you're trying to move forward, you, in fact, you are pushing. Sometimes you see that you are pushing the sand backward as you are moving forward. That is, the force is equal and opposite. So we're going to solve some calculations to illustrate that. Let me check my time. Okay, let me stop here and then we solve some calculations. All right.